because of the inability of an alkene to rotate around a double bond, see, this would be rotation around the double bond. Here, they're lined up so it's planar, and so the two p orbitals overlap. But if I twist the bond to rotate around the double bond, to twist the double bond, you would see the p orbitals no longer overlap, and so it would break the bond. Okay, so the pi bond cannot rotate unless you have a huge energy input. So this means that if I have a substituent here and a substituent here, it is different than if I have a substituent here and one on the other side, because you can't rotate to make them go to the other side. If I look at this further, alkene, you can see the two methyls are on the same side. I cannot rotate around this pi bond. So this molecule and this molecule cannot have the double bond rotate, so they can't interchange, not without a huge input of energy. So these two are on the same side of the double bond, whereas these two are on the opposite side of the double bond. I like to, if I'm in class, what I like to do is say, if the two carbons in the double bond for my elbow, the two methyls on the same side looks like a touchdown. Whereas if you have it trans, that would be cis if they're on the same side. If you have trans, it's like one elbow rotates and you have your hand going down instead of both being up in the touchdown position. So how is it you have cis? On the two carbons that are in the double bond, one group on one double bond is on the same side as the other group on the double bond. Whereas here, the two groups on the double bond, notice they're on different carbons, are on opposite sides. And we call these cis-trans isomers. For you to have a cis-trans isomer, you must have a hydrogen on each carbon in the double bond. See that? A hydrogen on each carbon in the double bond. Otherwise, it cannot be a cis-trans isomer. Okay, let's try this problem. Which one of these can be a cis or trans isomer? Either cis or trans. Look at it, try to figure out for each of these molecules, and then restart the lecture to get the answer. Okay, if I look at these molecules, let's just look at the top row. If I look at this double bond, there's only one hydrogen. If I look at this double bond, there's only one hydrogen. So neither of these can be a cis or trans isomer. Now this is a stereoisomer of this, because you can see they're the same connectivity, but this does not fit inside this one's space because these two groups are switched. But they are not cis-trans isomers. Okay, if I look down at this row and I look at this one right here, I can see these two ethyls are on the same carbon and these two hydrogens are on the same carbon. But this is not a cis-trans isomer. This has two hydrogens on one carbon. For it to be cis-trans isomers, you have to have a hydrogen on one carbon and a hydrogen on the other carbon in the double bond. So this is neither cis nor trans. Let's look at this one. There is a hydrogen here and a hydrogen here. If I look at this molecule, this can be either a cis or a trans isomer because the hydrogens are on each, there's a hydrogen each on the carbons in the double bond. And if you look, the ethyl is on the same side as the ethyl, so we can say this is the trans isomer. The one on the right cannot be, left, cannot be a cis or a trans isomer, but this one is a trans isomer. Which one of the compounds with the formula C3H5 has cis-trans isomers? Well, to do this problem, we actually have to draw this out. So if I draw these out, I would see that this is 1-chloropropene. See, this is propane, 1, 2, 3, ene on the number 1 carbon, and the chlorine on the number 1 carbon. If I look at this, this is 2-chloropropene. This is propene. There's a number 1 carbon. There's a number 2 carbon. So 2-chloropropene. And this is 3-chloropropene. Here is propene, number 1, number 2, number 3 carbon. If I look at these compounds, this one has a hydrogen here, and this one has a hydrogen here. This has a hydrogen, 2 hydrogens, but they're both on the same carbon. And this one, it has a hydrogen, and a hydrogen up here. It has to have 2 groups on the 2 separate carbons in order to be cis or trans. This is nothing, neither cis nor trans. So if I look, the only one that can have cis-trans isomers is 1-chloropropene. And if I look at this arrangement, the way that I've written it, this is cis 1-chloropropene. Sometimes we have more than 2 groups on an isomer. Sometimes, like in 2 slides previous, you saw there were 3 groups on there. When we do that, there can still be stereoisomers, and we need to be able to describe which isomer we have. And the way we do this is with the EZ designation. E stands for entgegen, which means opposite in German, and Z stands for zusammen, which means together in German. So when we have an E isomer, the highest priority groups are on opposite sides of the double bond, kind of like a trans. And when we have Z, the highest priority groups are together on the same side of the double bond as in cis. So what we do is we look at all the groups that are on the double bond and we prioritize them just as we did with stereochemistry in looking at chiral carbons. We use the Cahn-Ingold-Prelog rules, and we assign priorities to each of the 2 groups that are on each carbon. So if I look at 1 carbon in the double bond, I will say priority 1 and priority 2. I look at the other carbon in the double bond, and I look at the groups and say priority 1, priority 2. Then I look to see, are the 2 high priority groups on the same side? That would be Z for zusammen, or opposite sides. That would be E for entgegen. So we look to see how they are arranged in space, and then we can assign them E or Z. Let's look at an example here. Okay, let's go down here and look at this compound. First, let's name the compound without worrying about E or Z. To name the compound without worrying about E or Z, the first thing we do is we look at the carbon chain. How many carbons are in it? 1, 2, 3. Notice this is not a carbon here. This is a bond to the chlorine. This is not a carbon here. This is a bond to the bromine. So there are only 3 carbons in this, so we get propene. This is the number 1 carbon. Why is it number 1? Because the double bond, 1, 2. Where are the chlorine and the bromine? On the number 1 carbon. So we say 1 bromo, 1 chloropropene. Notice bromo comes before chloro because it's lower in the alphabet than chloro. B is lower than C. Now let's look and see, is it E or Z? So I go to this carbon and look at what's attached. Hydrogen is lower priority than methyl, so methyl gets a higher priority grouping. Then I look at the bromine and the chlorine attached to this carbon. This carbon has bromine higher priority, so this is higher. Now I look at how the higher priority groups are oriented toward each other. They're across the double bond from each other, so this gets the E designation. So E, 1 bromo, 1 chloropropene. Here are some more examples. This is really easy. This is cis-2-pentene. Lowest priority, highest priority. Lowest priority, highest priority. Cis-2-pentene is the same as Z-2-pentene. If I look at trans-2-pentene, the highest priority groups are opposite each other, so it's E-2-pentene. Go ahead and assign E or Z configuration to each of these molecules. All right, if I look at this, first we can go ahead and name these. Some of these we can, some of you won't be able to. This one I could name 1, 2, 3, 4, 5. So this is a pentene, 1,2-pentene. Then I could say 1-chloro, and then this is chloromethyl on the number 2 carbon. So it would be 1-chloro, 2-chloromethyl, 2-pentene. If I look at naming this as E or Z, I go to give it priorities. Ethyl is higher priority than hydrogen, so this has highest priority. Now I go over here. Oh, whoa, this one has the same priority as this one, so it's neither E nor Z. So I just call it straight name, no E or Z or cis or trans. If I go over here now, I look and I can name the alkene. This is hexene, and it is 3-hexene. And on the number 3 carbon, we have a chloromethyl group. So I would say 3-chloro, 3-hexene. Now is it E or Z? Ethyl is higher priority than the hydrogen, and this chloromethyl is higher priority than the methyl. So I see the 2 highest priority groups are on the same side. So this is Z, 3-chloromethyl, 3-hexene. If I look down at this group, or this compound, I can, we're not going to bother naming it, it's too complicated for you, don't worry about it. Okay, if we look at this, which is the highest priority group? This one is. Which is the highest priority group? This one is. See, this is carbon, carbon, then what? Nitrogen, nitrogen, nitrogen. What's this? Chlorine, hydrogen, hydrogen. Chlorine's higher priority than nitrogen. So this is the highest priority group. So now I compare how they're located with respect to each other. This one is on the opposite side of this one, so this is entgegen, E. If I look at this molecule, I will see, sorry about the oxygen being offset a little bit, move it over in your head. If I look at this, the highest priority group is this versus a hydrogen, lowest, highest. Then I look over here, highest, lowest. The 2 highest priority groups are on the same side, so it's Z, zusammen. Okay, and these words then confirm all the same words that I've just told you. All right, let's go on. Here's another one. Assign E or Z to each of these molecules. Okay, if I go to this molecule right here, you'll see that D is higher priority than H because deuterium is heavier than hydrogen. And if I look at this, okay, which one's higher priority? Carbon and carbon are the same, and then we have carbon, hydrogen, hydrogen, and here we have carbon, carbon, carbon. This is higher priority than that. So if I look at the 2 groups, they are entgegen, E. If I look at this molecule, higher priority, lower priority. Then I look over here, higher priority, lower priority. These 2 are opposite each other, so we say E, entgegen. So both of them are E.